Okay, so as I mentioned at the end of section 1.2, generally for PDEs, it's not enough to specify an initial condition at time 0. We also need to specify a little more information. Okay, and this is a theme that'll come up again and again. Kind of these boundary conditions can kind of very strongly affect the behavior and the properties of your solution. Okay? And so in this section, what we're going to do is give kind of a few examples of what some of these initial condition or boundary conditions might look like. Just give you a sense of what to expect before we really get our hands dirty in the future. Okay. So what do these boundary conditions look like kind of in the case study that we've been doing with the one-dimensional rod? So for a 1D rod, we need to prescribe our initial condition, right, which is u at time 0, and that will just some function f, as well as u at 0 and u at L of t for all time. Okay. And so in practice, these may not necessarily be just the values of the temperature at the endpoints. We can also prescribe the flux of the temperature at the endpoints and some combination of those, which I'll get into in a little bit. But here, make this a little more concrete. So here's our rod, x equals 0, x equals L. Okay. And it's a line segment between the two. So if we just specify this initial condition f of x, right? What I'm going to do is plot the temperature above the rod with the graph. Okay, so suppose the initial temperature looks something like that. Okay, and so the claim is that if you just have this initial condition, this initial temperature, and you have a rule for how it evolves in time, and the rule in this case is the heat equation, du dt is equal to k d squared dx squared. Turns out it's not enough. Okay, and maybe one way to see that is, right, we give one initial condition in time because we have one time derivative. Okay? In this case, we have two spatial derivatives, okay, that are, right, telling you how heat flows. And so the fact that we have two spatial derivatives suggests that we should have two kind of initial conditions in space, or we're going to treat them as kind of boundary conditions, okay? And we're going to call them boundary conditions. Okay. Cool. So what might these look like? So the first kind of form that these boundary conditions can take, actually, let me keep the picture here, is if we just say, here's a prescribed temperature that the heat profile has to have at these endpoints. What the temperature does in the middle, you know, we'll figure it out, see how it evolves. But we definitely want these temperatures at the endpoints. Okay, and so the book describes it as maybe you've the ends of the rod are immersed in, you know, fluid baths or some sort of bath that, right, keeps that temperature fixed. Okay, so heat can flow from the rod into the bath, but properties of the bath, whatever, mean that whatever heat kind of you're losing doesn't really affect the temperature there, just because the temperature at the end of the rod is whatever temperature that bath is. Okay. So what do these look like mathematically? So here we're saying U at one endpoint for all time, that's going to be some prescribed temperature. Okay, so this is going to be some other function, right? Your prescribed temperature at one endpoint. And this boundary condition can also depend on time. Okay, maybe the fluid bath that makes contact with this rod, maybe it's cold in the morning, hot during the day, cold at night in the morning again. I don't know. Maybe it changes. And we want to allow for that. But the key thing is that this condition doesn't really depend on space, because we're saying, no, we're just evaluating it there. Okay. And we can also do the same for the other end of the rod. So this might be a temperature prescribed at point L. This could also depend on time. Okay, so that's one condition. Another condition, let me copy this and bring it down. Copy. So another condition might be you have an insulated boundary. Okay. And what does this mean? Well, here's the rod. So if something's insulated, it means that nothing can flow in or out, right? Heat or energy can't flow in and out. Okay. And what is flow of temperature? How is that described? Well, that's given by, if you recall, this K0 of 0, right? So here, let me rewrite the law. So Fourier's law says the flux, some point in space and time, is given by minus K0 x, so some property of the material that tells you how stuff can flow, times the gradient of your temperature. Okay. And so if we have an insulated boundary, if we're saying, here's how, so maybe insulated isn't completely the right word, but if we're prescribing how heat flows in and out at the boundaries, okay, if it's insulated, no heat flows, so this condition will be 0. But maybe we want to specify how heat flows. Okay, so what we'll be doing is then we'll be saying that phi, say, at the endpoints, okay, this is going to be some prescribed function. And again, it can depend on time. Maybe you want to let some heat flow out for some amount of time, no heat flow out for some time, let heat flow out again, etc. So that's kind of this condition on the flux. Because of Fourier's law, we can relate the flux to the temperature. Okay? And so what that means is that instead of this flux term showing up right here, instead what we're going to do is we're going to say minus K0 of x, but we're evaluating, say, at the left end point of the rod, minus K0 that times the derivative of u in space. Let me give this a little more room. The partial derivative of u and x times this K0 at the left endpoint. This is our some specified flux. Okay. These come up naturally. We'll see these conditions a lot. On the other side, you'd expect it to look like the properties of the material that describe the flow at point L, x equals L, times the gradient of u evaluated at the right endpoint. This is going to be maybe a different prescribed flux. Okay. Okay. So what does this look like as a picture? Well, right, flux is a derivative, right? I mean, if you divide by k0 of L or 0, then move that to the other side. We're just specifying what the spatial derivative of temperature looks like, okay? And so we might draw that as something, it's not super clear, something like that, right? So maybe we're saying the slope of the temperature at L has to look like this. And then maybe the slope of the temperature over here has to look like that, maybe. Or actually, let me draw it like this. Maybe you're saying so much heat energy is flowing into the system like this, and no heat is flowing out over here. So that's how we might draw it, okay? But this set of boundary conditions is telling you, right, what the derivative looks like at the endpoints of the region, okay? Okay, and so kind of a third family of these conditions that we talk about, I mean, less so than these others, but is worth knowing. It's kind of a law of cooling, okay? And so if you recall, so Newton's law of cooling says that, right, maybe let me write it like this. Change in temperature over time is proportional to like minus K times the difference between temperature and some base temperature. Something like that, right? That you may have seen in another calculus course or in some other physics course. But it's just I guess, a law that Newton formulated, okay? But we can do a similar thing here, okay? So maybe, right, so what's happening is heat is flowing out of the end of a rod, okay, into some other space. But then the temperature at the end of the rod, we want to describe by this law of cooling, right? So what we're going to say is kind of this third family of boundary conditions is so how much energy are we losing at one of the endpoints, right? What's the kind of flux of the energy out of the rod or maybe into the rod, whatever your perspective, whichever endpoint you're looking at. Right, so what is the energy flux? Well, that's going to depend on the temperature difference between kind of that point of the rod and some base temperature outside of the rod, okay? So what does that look like? So we'll write it like this, minus H times the temperature at that point minus some base temperature outside, okay? This H here is just some, we'll call it like a cooling constant, okay? But otherwise, this is another boundary condition we can prescribe, okay? And so, okay, so notice that, oh, okay, so I'll write it again. Minus H U of 0t minus U at 0, or U sub 0 of t, and this was a cooling constant. Okay. So one thing we can do, maybe clear the minus signs, move things around, but this can also be written as k0 du 0t dx minus h u0 of t is equal to minus u0 of t. Okay. So This interpretation is maybe a little better physically. We can interpret it via some sort of law of cooling. This is maybe a little more comfortable mathematically, right? Because here, what we're doing is we have, this is an unknown or something related to our unknown function. This is something related to our unknown function. So maybe two like variables. And then, let me write it like this. So these relate to the unknown. These are constants. And then this is given. Okay. So this kind of looks like a linear system. Okay. And indeed it is. It's a linear combination of a condition on the derivative as well as on the actual function value, kind of at that boundary point. Okay. And so these will come up as well. So I gave kind of more mathematical names for these things. Or I gave more physical names and interpretations for these things. So I'll say generally these conditions are called, so if we're prescribing the function value at a point, this is called a Dirichlet condition. I've heard some people pronounce the name Dirichlet, like with the kind of K. I mean, it depends on how you pronounce this. I pronounce it as a sh. A lot of other people do, but it's beside the point. So if you're prescribing the function value, it's usually called a Dirichlet condition. If you're prescribing the function derivative, and this is going to be some given flux, this is usually called a Neumann condition or a Neumann boundary condition. And then the final one that I wrote was a linear combination. So C1 du at 0 t dx plus C2 of u 0 t. So C1 and C2, these are constants. So we're looking at a linear combination. If we say this is equal to some other function u0 of t, this we usually call either a Robin or a mixed boundary condition. Someone was named Robin that really worked with this stuff, hence the name. Okay. Okay, so yeah, these are the kinds of boundary values that we can expect. I wrote these all in terms of kind of the left endpoint of a rod. Replace that 0 with an L and you get the right endpoint conditions. One more comment maybe is that, of course, with special cases, we might say the value at the boundary, the temperature value at the boundary is 0. Okay, so this might be a prescribed 0 temperature. Okay. If we say there's no flux, this might be an insulated boundary. No heat can flow in or out. Okay, so you'd expect that there's no source, then the total heat energy remains constant. And that's something that we'll revisit. And then, of course, we can also say, well, kind of this derivative, 0t, plus some other constant of the function value, that's 0. Come up with a good physical interpretation. But I mean, it's okay. Yeah. Anyways, so we'll see a lot more of these boundary conditions, how they play out in practice. But this is just meant to give you a sense of what you can expect in the coming weeks and months.